that I could ask you. I could also ask you to order them from weakest to strongest, and so on and so forth. Okay, so that concludes the second part of our summary outline, equilibrium for weak acids. Now we're going to move on to water and talking about equilibrium for pure water. Okay, I love introducing this topic about water by asking anyone if they know someone with multiple personalities. Like maybe it's a personality disorder, I don't know. These things do exist in the real world, and I'm not trying to make light of them, but water in the world of chemistry has a personality disorder. It can be both an acid and a base, depending on what chemicals it's around. So if you look at this top reaction up here, when water is in the presence of a base, so ammonia, NH3, is a base, and when water is in the presence of a base, it's going to act like the acid. What that means is ammonia, the nitrogen here, has a lone pair. It's going to grab a hydrogen from water, which is the acid. Remember, the acid is the proton donor. And it's going to make the ammonium ion, NH4+, and what's left over from water, the acid, is OH-. Okay, and we'll write conjugate here. These are the conjugate acid and the conjugate base. However, if you look down here at the bottom reaction, whenever water is in the presence of a really strong acid, such as HCl, it's going to play the role of a base. So water can be an acid or a base. These are just examples. Okay, here if water is the base, it's grabbing this hydrogen from HCl, making the hydronium ion. This is the conjugate acid. And what's left over from the acid is Cl-. This is the conjugate base. All right, so just to prove our point, water can act as an acid or a base. So what's the importance of that? Well, to get even weirder, it can play the role with itself. So I've been saying, well, depending on what's around it, it can be an acid or base. Well, guess what? Even if it's the only thing present, it can be an acid or base with itself. So that's kind of weird, right? So this one water molecule maybe says, hey, I want to be an acid when I grow up. And this water molecule says, okay, great, I want to be a base when I grow up. And if that's the case, you have one water molecule acting as an acid, one as a base. They're just going, this acid molecule right here is going to give its hydrogen. So we have lone pairs on this oxygen. It's going to grab a hydrogen from that water molecule and create a hydronium ion, which is the conjugate acid. And it's going to create a molecule of OH-, which is the conjugate base. Okay. Now here's the deal. Because water is not a very strong acid or a strong base, it's actually a really, really, really weak acid or a really weak base. If we were to write an expression for equilibrium, because notice we have a reversible reaction here. Okay, K for this reaction is extremely small. And remember, the larger Ka, the stronger the acid. So really small Ka means a really weak acid. However, any aqueous solution, okay, does this to some extent. Okay, water molecules can trade hydrogens to some extent, but it's just a very small extent. So if we write out an expression for K right here for this reaction with pure water. This is only for pure water. I want to make that clear. Here's the expression we would get. Remember, these are the products. So we have the concentration of H3O+ times the concentration of OH-. And here's our reactants. Okay? But remember, K is really, really small. So what that means is we have a whole lot of reactants and very little products. We have a large number on bottom, so this is a large number. And these are very small numbers. Okay, so we don't get very much of our products. We have pretty much all reactants. And that's further explained. I don't even know what I just drew. further explained by this statement here. Because water is both the solvent and reactant, remember its concentration does not change significantly in the reaction. So just like we did for Ka, we remove water from the K equation. Now we're not calling this Ka because water is not a weak acid. It's a really, really, really weak acid. We are going to call this something all on its own. When we take water out of the equation, what we're left with is just our top part, right? H3O plus times the concentration of OH minus. We're going to use a little W down here to indicate and remind ourselves that this equation only applies to pure water. And what we call Kw is this right here, the ion product constant, and it's just for water. Why do we call it the ion product constant? Well, this is the positively charged ion. Here's the negatively charged ion, and we're multiplying them. And when you multiply things, you call it the product. So it's the ion product constant for water, and that is Kw. Okay, so let's recap. We have Ka and Kw. How are these two different? Let's start with Ka. First off, Ka is for the dissociation. Let me erase. Ka is the equilibrium expression for the dissociation, I'm going to abbreviate, of weak acids. For example, the way we write this out is, here's our weak acid, HA. It's in an aqueous solution, which is water. We get a double arrow, and that is going to make the H3O plus and A minus, okay? And when we write out the expression for Ka, we get products, concentration of H3O plus times the concentration of A minus. These are our products divided by the concentration of HA. Remember, we don't include water. Kw is the equilibrium expression for the dissociation of pure water. Kw is when you have this reaction, H2O plus H2O, and we're going to make H3O plus and OH minus. And the value, Kw, equals concentration of H3O plus products, and that's it. We don't write over the concentration of water because we don't include water. Okay? So know these two things. Know how Ka and Kw are different. Know the equations for these. These equations, Ka and Kw, will not be given to you on the exam. You need to memorize them. Let's just write that down. Memorize. Memorize. You need to know these for the exam for sure. Moving on.